Wow, half and half, huh? Mass. Okay, this one we will explain it soon. Okay, the question was by mass analyzer, not mass spectrometry. If you inject glucose into mass spec machine, then it will be ionized. Then it can be analyzed. Analyze itself cannot detect neutral, the neutral material. Only charged material can be detected. Okay, in the electric field, it will travel still forward linear motion, not the coupling motion. Only in magnetic field, it will move in coupled way. Mass spec에서 또 뭐죠? Ionization, analyzer. Okay? Ionization method, ESI, EI, MALDI, those are the ionization. Time of flight, quadruple, ion trap between, but anyway, these are analyzers. Okay, electron ionization, MALDI, ESI, these are ionization. MALDI detector is one kind of ionizer. 내가 말린 아니라고 스팟 해야 있어서 안 된다고 그러지 않았어? HPLC에서 나오면은 그냥 애시드에 섞어서 스프레이 해야 된다고 그게 딱 몸으로 이렇게 쫙쫙 흡수가 안 돼? Okay, MALDI you need the spot. That's why it's difficult to be directly connected to the HPLC. If you want that, take the sample, spot one by one, then you can go to the MALDI. Okay? MALDI is ionization, ESI is ionization. So just ionization itself cannot make mass spec. Mass spec should have ionization and analyzer. Okay? Okay, MALDI is not analyzer. So it should be MALDI top, not top MALDI. other ion. Ion can be detected. We can see only exact mass, not molecular weight. Molecular weight means it's the average value of isotope combined together. So these two are the same. And we can see sometimes n plus 1, 2n plus 1, or n plus 2 divided by 2. Everything we can see. Okay, so today we move to the next topic of infrared spectroscopy. And I invited Hoyeon to present this. So, Hoyeon, please welcome Hoyeon.
Hello, I'm Kang Hoyeon, and today I'd like to present about IR spectroscopy. IR means infrared light. Before we start studying IR, there is something important to know. Last class we learned mass spectrometry, and today's class we will learn IR spectroscopy. Spectroscopy and spectrometry look similar words, but they have exactly different meanings. In the word spectroscopy, the term of scopy means observation, and it also means using light. We can find this term in some method of using light. For example, microscopy and telescope. And the term of spectrum means using spectrum. And in the word spectrometry, the term of metry means measuring. And in this case, a spectrum does not mean using spectrum. It means that we can measure from small mass to large mass when we use mass spectrometry. So the important point is that the spectroscopy and spectrometry is different word, and IR is spectroscopy, not spectrometry. Let's get into IR spectroscopy. If the molecular formula like CH4 is given, we can predict the molecules connection like this. But if the molecular formula like this is given, there are isomers. And another example, if the molecular formula like this is given, we cannot predict the structure of a molecule. If we use mass spectrometry, we can only know the molecular formula of the molecule, not the structure of a molecule. But IR spectroscopy is one of the good way to analyze the structure of a molecule. IR spectroscopy is the method of using light, and as the name IR spectroscopy indicates, light in the infrared range is used. Depending on the range of light that observed by molecule, the type of energy that is transferred to the molecule depends. For example, if the molecule absorbs X-ray light, the energy that is transferred by molecule is the type of bond-breaking energy, and a molecule absorbs infrared light, the type of energy will be vibrational mode energy. Also, IR spectroscopy is method of using vibrational motion, and IR spectroscopy is the method of using absorption, not scattering or emission. Various lights can be used to understand the structure of various molecules. There are many methods that using light. For example, X-ray photoelectron spectroscopy and UV visible spectroscopy, Raman, IR spectroscopy, and NMR. Before I told, IR spectroscopy is the method of using vibrational movement of molecule, and we can divide vibrational motion into 6 types. 2 are stretching and 4 are bending. In the case of IR spectroscopy, the stretching movement has a great influence. If molecule is stretching, the dipole moment of the molecule can be changed. Let's consider the molecule CO2. CO2 is a symmetrical molecule and it has a linear structure. If CO2 molecule is stretching symmetrically, that dipole moment will be zero, so we cannot observe it by using IR spectroscopy. But if CO2 molecule is stretching asymmetrically, dipole moment can be changed so that we can observe it by IR spectroscopy. Let's talk about the useful IR range. The wavelength is from 2.5 micrometer to 25 micrometer, and the wave number is from 4,000 to 400, and the frequency is from 1.2 times 10 to the power 14 hertz to 1.2 times 10 to the power 15 hertz. We can see in the picture of the bottom, of the top, if we know the wave number by IR spectroscopy, we can know the connection or groups that molecule have. And we can see in the bottom picture, we know that IR molecular vibration is not the energy transition between two different orbitals. This is the real result graph of IR spectroscopy. If we see the new data, we have to see the axis first. In this graph, the x-axis means wave number and y-axis means transmittance. So the best observance part is the part within the lowest transmittance, like this. And the stronger the bond, the lighter the atoms are joined together, the larger the wave number. To sum up, the information shown by IR spectroscopy is about what bonds molecule have, and when there is a change in the dipole moment, the change is seen in the graph. But IR spectroscopy has some limitation too. First, we cannot see all the bonds, and second, if sample is wet or not dried enough, OH peak is seen in the range over 3,000 wave number. Thank you for listening to my presentation.
Any questions for him? Okay, if not, I will start. Okay, today we are going to study about the spectroscopy. And she explained what's the difference between spectroscopy and spectrometry. The word of the spectrum, using spectrum, the word of spectrum came from this kind of bundle of different color range. So hold together this bundle is called as a spectrum. Where can we see this kind of a spectrum? In nature. Sun is white.
Rainbow.
In rainbow. The white light is divided into this range, and then it shows all color. If it's defined by wavelengths, all the color can be seen. So that is full color series. So that's in the beginning. It's called as a spectrum. Spectrum means a bundle of visible light that was originally given. How can you make a spectrum in the lab? Using prism. Starting from the white light, and then using prism, you can get those full spectrum. So originally, the meaning of a spectrum was part of this different wavelengths of light only for this visible light starting from about the 400 nanometer to 700 nanometer range. This was the original meaning. But now this was changed as a metaphor. Spectrum, political spectrum, very left wing to very right wing, kind of a metaphor. So that means the spectrometry, mass spectrometry, is that spectrum is just kind of a metaphor. It's covering all the range of molecular weight, not spectral wavelengths. Okay, that's kind of a change in meaning. So that's why in mass spec we use magnetic field and we use ionization method. We don't use any light there. Okay? So spectroscopy in Korean, what is spectroscopy? 몰라? What is the Korean word for spectroscopy? 성찬아? 알아? Spectroscopy in Korean? 설마? 봉광학. So 봉광학 means, 분 means split, 광 means light, 학 means study. Using type of a selected wavelengths of light, that is a spectroscopy. Okay? That means any kind of light here, electromagnetic wave, very short, gamma ray, or X-ray to radio wave, any of those selected wavelengths of electromagnetic wave is involved, then that's what we call a spectroscopy. That's very similar to our vision. Okay, our vision, we have 5 senses. So for 1 minute, close your eyes and listen to me. Relax, close your eyes. The information we get from vision, 있잖아, 공감하더라니까. The information we get through vision is huge amount of information. They say it's occupying more than 90% of all the sensing is focused on that vision. Only 1 minute if you close your eyes and relax, now you can feel other senses, which is only 10%. Those senses becoming more and more sensitive because the brain function is allocated to other functions. Usually we are very busy to analyze and process those information coming through our eyes. Now open your eyes. So this information is a very high quality information and a lot of information coming to our brain. That's why it occupies the 90% of our information processing of the system. Exactly the same way in analytical chemistry. When we analyze the material, most of the sophisticated methods, usually we use these light sources. Depending on different the wavelengths, let's just say X-ray, Hoyon said it can break the bond, that's true, but if it's very rigid bond, like X-ray diffraction measurement, if you have single crystal, and if you radiate X-ray there, you can get the diffraction pattern. You can see directly three-dimensional structure of the molecule. X-ray diffraction, is that spectroscopy? X-ray spectroscopy? Yes, it is, because you use the X-ray. That's part of electromagnetic wave. If you use UV visible, UV spectroscopy, visible spectroscopy, radio wave spectroscopy, those are all spectroscopies. That means our eye can see only very narrow range of light here, but using machines, using different detectors, we utilize all the wavelengths. Any part of those light, if we can use, we can open up new technique or new vision through electromagnetic wave. Seems like we utilize this one naturally, and UV a little, X-ray a little, but not every point here we covered yet. Maybe partially because we cannot generate those light efficiently. One of them is around here, terahertz range. It can be used for visualizing somebody behind the wall. So those range of light we didn't have a chance to study yet. So that means depending on those light wavelengths, there may be new studies is possible. The irradiator, the accelerator in first phosphet, it generates all kinds of light in a very strong intensity. It is accelerating the electron, and then that the accelerated electron generates all kinds of the wavelengths of light, and that's why through this circle there is a 20-some numbers of different labs. They picked out different wavelengths of those light, and you can do different experiments. Okay? That's the power of a Baksa-Bak puzzle. So today we learn only this part, infrared part, something we cannot see outside of our visual the range. We can see from 400 nanometer fluorescent violet to 700 of the red color. Right outside there, that's the range is the infrared, and those are the electromagnetic wave. So here this is the amplitude, and wavelength is starting from one peak to another peak. This is wavelength. So wavelength wise, longer than 800 nanometer, that could be infrared. Now if you look at here, wavelengths can be defined as a length, and this is a visible light, and these are all together, this is infrared. But if you divide them further, okay, further we call this is a near infrared, this is a far infrared, this is maybe middle infrared. So near infrared means near to what? Near to visible light, okay? Near to what we can see. Now, near infrared, far infrared, which has a higher energy? Near infrared, because the wavelength is shorter, frequency is higher, speed is the same. What speed is it? Speed of light, right? Speed is the same. Now, if you apply the same thing to the UV, near UV and far UV, which one has a higher energy? Far UV has a higher energy because it's far from visible. It's a far UV, and this is near UV. Sometimes we use a little different term, deep UV. You think deep is far or near? You think it's near? Okay, this is surface. So this is shallow. This is deep. Is it far or near? Yes, that is a far. Okay, sometimes we call far UV or deep UV. That means that can be further the far from our standard visible light. So in IR spectroscopy, usually we use this range. That range is visible light. The boundary is about 700 nanometer. We start to use here 2.5 micrometer to 25 micrometer range. So this range. 2.5 micrometer is what nanometer? Say again? Say again? 2.5 micrometer is one number in nanometer. 2,500 nanometer. Okay, 2,500 nanometer. That means 700 nanometers here. Okay, this range we don't use much. This range is we use more in optical imaging. We don't see that, but the machine can detect and it can make it image. Especially in battlefield, you see the night goggle. Now with the night goggle, without the light, you can see the enemy's motion. Right? They detect those hit. Those are the near IR range here. By the way, that color, if you have the night goggle, usually what's the color?
Green.
It's usually green, right? Near IR, we cannot see. How can it be green? Green is 500 to 20 nanometer. Why can be green? Yeah, most likely those machines, night goggle machine, we don't use red. We don't use blue. Most likely we use green. Why green? How come you can see the green color from infrared?
Computation.
That's a calculated artificial color and just made those detected signal converted into visible light and make us to you can see. And why green? It's the most sensitive color we can see because the white light, the peak is from the sun. This peak is yellow to green range. That's why green color we can see most sensitive. Okay, so we used this range for organic molecular analysis. Now, if you need to call like wavelength wise in centimeter, 2.25 multiplied by 10 to the minus 4, 2.5 multiplied by 10 to the minus 3, that's too long to call. If you change that into here, 2.5 or 25, maybe it's also possible, but to make it easy to convert, we change that into, this is wavelength, and reciprocal to this wavelength, centimeter minus 1, and converted it. Then this is wavelength, and then reciprocal to that, this is a wavelength. Sorry, this is a wavelength, and this is a frequency unit. Okay. Specifically, for centimeter minus 1, this is what we call wave number. But the unit is frequency. If it's the wavelength, the shorter, higher energy, correct? If it's the frequency, the higher energy. Okay? So then, this range, 2.5 is about 4,000. And lower side, 2.5, 25, what's the difference of energy difference? 2.5 to 25. Energy difference? Twofold? Threefold? Energy difference of 2.25 to 25. How many fold? That's 10 times. And if you convert that into frequency, this is 4,000 to 400. 4,000 is 10 times stronger energy than 400. This energy is mentioned, so if you plot them, as you can see, so about 400 to around 4,000, this range is usually used for IR spectroscopy. And in IR, this side is a higher energy, this side is a lower energy. So if you say, okay, I learned IR, then I would ask the question, what is the x-axis unit? Centimeter minus 1, that's a wave number, and that's a frequency. That much you need to be able to answer. Okay? And y-axis, already when you explained, this is transmittance. Means if the spot is here, no absorption. If the spot comes down, it's a high absorption. And we also explained the visible. Visible means we see. And we see as a color. Okay? So those color change happens when electron is on ground state and when it is excited. So this change we call electron transition. Electron transition most likely in UV range or visible range. Those range we can see. So the first chapter next semester you will learn UV visible the spectroscopy. And usually you see one broad peak. And depending on those wavelengths you see the color. Any colorful material you can use will be visible, similar to our eyes. Infrared we cannot see, but they measure this kind of motions, as William showed. So those motions moving like this, or moving like this, or moving like this, moving like this. Any kind of those motions, there are higher mode and lower mode, and they can absorb the light. This is also quantized. That means motion is not smoothly moving like this. The motion is like this. It's quantized. Okay? So those motions can be detected by higher range of absorptions. Now, we need to be familiar with those IR spectrum. And 400 to 4,000 range we see. And we are learning right now organic chemistry. If it's physical chemistry or other inorganic chemistry, your target material may be HCl. Those motions may be much simpler. You can see very sharp one peak. Organic molecules, we have carbon and hydrogen. And CH bond is very common. So this is very typical organic, the alkane molecules. Alkanes, one unit party is about from this 3,000 range. And a little lower than 3,000, there are a lot of peaks. Those peaks are coming from CH vibration. So alkane molecule, of course, there may be many CH. C and hydrogen, they are vibrating. So that vibration is about a little less than 3,000. 29,000, 2,900 or 2,800. Those kind of many peaks. That's why there are many other peaks coming together. If you see this peak, oh, this molecule is an organic molecule. Okay? This has a lot of CH. Now, among them, if this peak is from sp3, this is all sp3. If it's sp2, okay, S character is a little bigger, then H can be a little further attached to the carbon side. So this is a little more difficult to vibrate. Then it becomes a little higher energy it can observe. Then you can see one stick out. So that peak is about 3,100, 3,100. Okay. 이러면 알겠지? $3,000, 2,900, or you can make it 2,900. Okay. 3,100, 3,100, or 3,100. Okay. So there is a peak a little stronger than this. Then oh, there may be double bond and H there. Okay. If it's triple bond, maybe it's becoming even stronger, about 3,300. So this is something unique, you can see. All others is difficult to see. Another thing, now carbon-carbon bond vibration usually comes from here, around here. This is carbon-hydrogen vibration. Okay, 3,000, a little higher, 3,100, 3,300. Carbon-carbon vibration. Organic molecule, of course, there's a lot of them. That's around here. And if it becomes a double bond, it comes a little higher. Originally it was a 1,500, now this is about the 1,600. Triple bond, getting even stronger, 2,200. Okay, so these are organic molecules. Okay, look at here. Okay, it's alkane. Maybe alkene, maybe alkyne. And triple bond, usually this range is very clean. This range is quite busy, but this range is very clean. Now, triple bond gives you quite a unique peak there. CN triple bond or CC triple bond, about the 2,200. Now, summarizing, CH bond is approximately 3,000, but it's a sp2, 31, sp3, 33. And OH and H is usually a little stronger than CH bond. H is a little further attached to here. And CC bond goes around here. Now this range is quite difficult to follow. There are many things that are the complex, the signals are coming from here. That's why usually this range we don't annotate. But different structure can give very unique pattern like fingerprint. That area, usually we don't assign, but if you compare two materials, and one material has one fingerprint, the other material has another fingerprint, and just by comparing those two, and use them as if this is the same material or different material. So in criminal site, if I have a tire, the scar, and you take those tire material, and take the IR spectrum, and then compare with the different product of the tires, then if they match those patterns, it's not analyzing by assigning, just by looking at those patterns after we see our fingerprint. Then they match, okay, this is from the type. Okay. So important information is this one, and also triple bond is about 2,200, and double bond about here or here or here, you see. Triple bond, 2,200, double bond about 1,600, and then CC bond is even further down. Now alkane, I said this CH is less than 3,000, and carbon-carbon bond is in fingerprint range. Alkene, now this one is a little high than 3,000, 3100, double bond about 1600, and the rest forget about it. Alkyne, CC triple bond 2200, and CH bond 3300. For the here. I'm repeating same things over and over. Those are the organic molecules' general features. And this is sp2, it's a little higher, but if it's in the aromatic ring, then it's quite big. So usually we don't see there is something big. Now, important thing, alcohol. CH bond is usually less than 3000. Now, OH is stronger, it's quite broad. So if you see above 3000, very broad peak, you suspect it would be either alcohol, OH, or water. If it's a wet sample, then you will see very broad peak, like this. If you look at here, okay, this is organic molecule, and the other part is mixed up here, so usually this range we don't count. And it's very clean here, there's no triple bond. And here is the broad above 3000, broad 1 peak. That's OH peak. If it's NH, OH peak broad and strong. If it's NH, especially it's a 2H, then usually 2H then 2 peak. It's a medium size and less broad than OH. And those peaks are NH peaks. So NH peaks a little higher than the 3000, which is a medium size, a little sharper than OH. Okay. Now this is important. In IR, this peak, 1700 range, very strong, sharp peak. Dose peak is CO double bond. In IR, CO double bond is strongest and also very critical and very unique peaks. 1700 sharp peak, then your first guess is carbonate. Either aldehyde or ketone or ester, and all of them is a very similar range. Depending on other groups, it can be a little changey, but all of them is a very strong, this kind of peak. 1700. Then you say, okay, there is a carbon group. This molecule, now if you look at here, okay, this is an organic molecule, and there is some other peaks here, and okay, this molecule should have carbonate. This is the molecule. Okay. Now triple bond. There is a triple bond, very unique peak is here, this peak. And CH peak here. There is no alkane peak, that's why it's a very weak around here. 3000 range here, there should be alkane, but there is no alkane here. And this peak coming here, and triple bond can come. CC bond, CC triple bond, and this is CH bond. 33,000. Okay, one molecule is a cyclohexane. The other molecule is a cyclohexene. Can you distinguish which one is which? Because? By which peak? Seven and?
This one and this one.
The other important one?
It will be this peak.
Yeah, that one is a good peak. That's the CH from here. CH summarize this, you can see if you study IR, to summarize this, if you see a little lower than 3000 range, okay, this is alkane, organic molecules. And if you see very broad peak above 3000 OH, there's a little sharper and medium peak in H. But these two are most important. And critical one, as I said, carbonyl peak, 1700. Very strong one. And if you add 7 more, CC triple bond, alkyne, 2200 and 3300. Those are very characteristic peak. Alkene, this peak, as we have seen, 3100. Also representative. So in IR, when IR was invented, Poyon showed a very good example. If you look at molecular formula, we have practiced several times. You can draw many isomers. Those isomers, especially if it has oxygen, those isomers can be like this form or like this form or like this form. Now, using IR, IR's information is some unique functional group. Here, among this separate one, you can say, okay, maybe this is the option. If there's a OHP, this is not option. And then we can rule out these possibilities. And whether there is triple bond or not, or CO double bond, there's no CO double bond here. The lone of isomer of this it would be it's 4 carbon, then this can be one possibility. Okay. So if there is a very strong CO double bond, then you can choose this one. If you don't have that, this is also ruled out. So IR gives you the evidence of existence of some functional groups. And if they are in the very mixed area around here, fingerprint area, then it's almost impossible to find them. But very unique part here, carbonates. And triple bond, 2200 and 3300, and double bond, this one and this one. So those kind of some clue from the molecule we can get from IR. It is helpful, but of course if it's a complicated organic molecule, it gives us quite limited information. But historically, this has been used for quite a long time before this technique has been developed. NMR. So this is the topic we are going to study next week. What is the abbreviation of NMR? Do you know? Okay, the abbreviation of NMR, nuclear magnetic resonance. Dawn promised to teach you the very fundamental knowledge of NMR next week. And this technique, especially for organic molecules, this technique is so powerful. This has been invented in the middle of the 20th century, 1950 or something like that. It made 3, 4, 5 Nobel Prizes and developed further and further. It's so powerful, especially for organic molecule structure. So people said NMR no more research. If you take NMR, you can get the structure. So that technique we are going to study next week. Okay. So we have next week 2 days we are going to study, learn basic NMR, and then how to utilize those NMRs, combining together with the mass spec and IR and NMR spectrum. And by looking at those spectrum, then how to analyze those structures. I give you one molecular formula, and then give you those spectrum from different techniques. And using those information, and we figure out those molecular structures. Okay, let's summarize quickly one more time over this. So here, what about the shows? Okay, IR, we don't get many informations, but from IR, what we can get, alkanes, alkene, alkyne. Usually IR, this area is clean area, so this is quite unique filter boundary. If you see this broad big pig OH, or your molecule is wet, you did not fully dry your sample. Water is there. And if you see the two peaks, you can suspect NH2, but this is a medium size. Alcohol is much stronger. And most unique part is this one, 1700, 1700 of carbonate. It can be aldehyde, ketone, ester, amide. It's shifting a little, but it's exactly the picking up whether what kind of functional group is difficult. But anyway, CO double bond. That's the strongest peak you can see from here. Ketone, ester. Now this peak, oh, carbonated. This is one of them. Triple bond. This one, 2200 and 3300. And this is alkane, this is the alkene. Okay, not many information we can get from IR. Looks like the whole table is quite complicated. Actually, it's almost like a decoding, you know, the this is encoded some message, and by utilizing this table, you can match one by one. But if you look at the spectrum right away, the major information you can get is there any OH or carbonyl or triple bond or double bond? Most likely that's the information you can get from IR. Okay. So now I gave you selected some problems from textbook to try to match that for the mass spec or fragmentation pattern and IR for making yourself familiar with those techniques. You may not use this technique very often, but very basic one is very good to know that you can communicate with it. Okay? Any questions for mass spec or IR?
Is there any reason of using x's of as wave number?
To make always when we decided this kind of a unit, to make it easy for us to use and report and read. In NMR case, we either chose from 0 to 10. But this is the easiest option. In IR case, if you pick up 0 to 1, 0 to 10, then our unit may be here. This is a 2, and this is 2.5. Now we don't want to say 2.5 much. Then maybe 0 to 100. That's the option, right? 0 to 100, then 22 or 23. Sometimes we need to say 22.5. So then, to avoid those point numbers, and okay, sometimes we need to distinguish those numbers. When this was the original method, we need to distinguish these terms. So that's why maybe 1000 may be good number. Then we can, without using the point, we can distinguish 5 and 6 or something like that. That's why it is used 10 number. That's one guessing. For centimeter is the proper range for that. If you use the meter, then this becomes 17.15. Now it's more difficult. So centimeter is familiar to us, and converting them into this number may be easy to use. That is the main reason we guess. But most likely those are kind of the first scientists that they chose to use that unit, then everybody followed. That's another reason. Okay, another question? Okay, now we are almost near to the animal is the last chapter we study. Okay, so reviewing those the organic the chemistry part is one way, but for this week we can try to focus on those technical part. Fortunately, we have a 1 week saved for the last week, so we have a chance to re-review all those reaction part after the Middleton exam. So for the final exam, you are not going to take for the Middleton exam, the result mainly focus on the after Middleton exam, so you can focus on better on there. Some of them may be a little related, but mainly from the after Middleton exam. That means we didn't learn too much. We learned a little about the alkene here, but majority of alkene chemistry, alkyne chemistry, and alkyl halide chemistry. That's all we learned. Okay, and two motion parts. Okay.